Hello, everyone, and welcome back to your favorite algorithm channel with your favorite programmer Ryan. Uh, so today we're going to be doing LeetCode 17, letter combinations of a phone number. This is a pretty fun one, so this should be good. So let's introduce the problem. Given a string containing digits from 2 to 9, inclusive, return all possible letter combinations that the number could represent. So here's the keypad. So it's just kind of just like a phone number or a telephone keypad. And so each number corresponds to a certain number of letters. So if we look at the example down here, it says that the input is 2, 3, and the output should be an array. So we should be returning an array. And you can see that these are all the different possible combinations. So A, D, A, E, A, F, so on and so forth. So the first character represents all the possibilities from pressing the 2 key. The second character represents all the possibilities from pressing the 3 key. So as always, I encourage you to try to solve this problem on your own first. And when you have a solution, or if you get stuck, come back and watch the video. So if you're ready, come with me to the whiteboard. Let's start out by solving kind of just a visual representation of this problem, like a visual representation of how we would solve this problem. So I have a pseudo object here on the screen, which is our letters object. Our numbers 2 through 9 are mapped to their specific characters, which are in an array. And then up here at the top, we have 2, 3, 4, which is just going to be our input string of numbers. So we would start out with just an empty string, right? And then from that empty string, our first input number would be 2. So we would go through and add 2, add all the letters for 2 as our possible solutions, right? So we'll create 3 branches off of our empty string, one for A, one for B, and one for C, representing all the possible first characters that we could have. So for all of these characters, each one of them is going to have another 3 branches themselves. So we'll go ahead and put those 3 branches on, and we're going to have, let's see here, our second letter is going to be 3. So we're going to have A, D, we're going to have A, E, A, F, we're going to have B, D, B, E, and B, F, and we're going to have C, D, C, E, and C, F. So that will take care of the 3. And then then we're going to move on to 4. And then for each one of our leaves on this kind of tree structure that we're creating here, that's a keyword, a tree structure, we're going to create 3 more branches. So we'll go ahead and create 3 more branches, one for each one of our leaves, and we'll go through the letters for 4. That would be G, H, and I. So we'll go A, D, G, A, D, H, A, D, I, A, E, G, A, E, H, A, E, I, A, F, G, A, F, H, A, F, I, and so on and so forth. So for each one of these leaves, we are appending every possible letter to each one of those solutions that we've been building up so far. So this is kind of the key, right? So what does this look like to you? To me, this looks like a breadth first search approach, right? We're kind of starting with nothing and then gradually building up all of our solutions, right? So that's the coding strategy that we're going to use to solve this problem, is breadth first search. All right, let's do a quick run through of kind of how this would look in code. How would we take that tree structure and implement it using some kind of data structure in code? So we'll start with our string here, 2, 3, 4. And again, I've drawn like the pseudo object on the screen here, the letters object, the numbers that correspond to the array of characters. So we'll start out here with our string 2, 3, 4, and we'll start at 2, and that is going to be the letters A, B, and C. So the first thing we're going to want to do is iterate through this, and we'll add A, B, and C to our array. And then the next time through, now we're going to increment our pointer to be set to 3, right? And 3 for our letters object is D, E, and F. So we'll start at D, and we'll start adding D to the first position, all the A's, and then E, and then F. And then we'll do the same with B, BD, BE, BF, and then finally C. So we're just kind of building our answers as we go. So now we're done with 3. And then finally we'll move to 4. So 4 is G, H, and I, and we'll start adding G to H and I to AD. We'll add G, H, and I to AE. We'll add G, H, and I to AF. And then we'll keep moving along, adding G, H, and I to each one of these strings that we're building up here. And I just kind of want to run through this quickly just so you can kind of see like how these answers are getting generated. So then we'll add to CD, GH and I, to CE, GH and I, and then finally CF, GH and I. Let's talk about the time complexity of this problem. When we first start out, we have 0 answers to our problem. After 1 iteration, we have 3 answers. 2 iterations, we have 9 answers. And then after our 3rd iteration, we have 27 answers. So what does this look like? Well, we're multiplying by 3. So 3 times 3 is 9. 9 times 3 is 27. And we're doing this how many times? We're doing it n times. So we're multiplying by 3 n times. So that's 3 to the 1, 3 to the 2, and then 3 to the 3rd. So this is, and we're also iterating through our digit string, which is n. So that is going to be big O of n times 3 to the n, right? But what if we were just using digit strings that included only 7s and 9s? Well, if you look at 7, you can see that there are 4 characters in that array. So that wouldn't actually be 3 to the n. That would be 4 to the n. So in the worst case, the complexity of this problem is 4 to the n. And because n, multiplying n by 4 to the n is not really going to determine the upper bound of this problem, so we can just say that it's a big O of 4 to the n. Now what about the space complexity? Well, we are using an array to gather up all of our answers. So if we're including our answer as part of the space complexity, then you could say that the space complexity is also 4 to the n because we're also generating that many answers through every single iteration. But if we're not including the space complexity, we're not using any extra space to generate our answer. We're just generating our answer using this array. So if the array is included in the space complexity, then it would be the same as the time complexity of the problem. I've gone ahead and added the letters object with the corresponding numbers and their character arrays, so we can just get started on coding up the letter combinations function. So the first thing we want to do is just check to make sure that that we've actually have digits, right? So if not digits, then we'll just return an empty array. Otherwise, we'll just go on with solving the problem. So we want to initiate a combinations array to track all of the combinations that we're going to be generating. And we can just go ahead and spread in the first characters so we don't have to iterate through them in the rest of the function body. So we can just say at letters and digits, and we'll just grab that first character, and we'll just spread those first characters in. And then what we want to do is just start iterating over the digit string. So we can start at the first position because we've already spread the first digits characters into the combinations array. And then while I is less than digits dot length, then we'll just increment I. So what we're going to do here is we're going to create an updated combinations array. So we'll iterate over our combinations, and then we'll push all of our new answers into updated combinations, and then we will reassign combinations to be updated combinations at the end of every loop. And the reason why I'm doing this is just because it kind of simplifies not having to deal with, pushing something into an array that we're iterating over, right? We don't want to do that because then we would just be iterating over that array forever. So then what do we want to do? We want to iterate over the combinations. So we could say combinations.for each combination. And what do we want to do with each combination? We want to grab the current letters. So that's letters at digits I. And then for each letter, we want to push into our updated combinations dot push. We want to push in the current combination plus the letter. And then after we do this loop, we then want to update combinations to be updated combinations. And then at the end, we'll just return combinations. So what did we do here? We check to see if there's actually a digit string. If the digit string is just empty string, then we just want to return an empty array. And then we initiated a combinations array with the first character's digits inside of it. And then we looped over the digit string, and we defined this updated combinations array to then loop over our combinations, and then for each combination, grab the letter at the current digit and append that letter to every single combination that's currently in the combinations array. And then here at the end, we're just reassigning combinations to be updated combinations, and then just returning our answer here at the end. Okay, we've got an error. Let's see. Last executed 2.3. Updated combinations dot push. Combination is not defined. Here we go. Oh, looks like I have a wrong character in here. Let's try one more time. All right, great. That took a while. Okay, so runtime 48 milliseconds. Great, faster than wow. We're the fastest code ever to be submitted to LeetCode for this problem. That's gotta make you feel good. But like I said in previous videos, I take this stuff with a grain of salt. So we don't need to look at the solutions. I think this is a really good solution to this problem, and I hope you enjoyed this problem. This is actually a really fun problem, I think. I really actually enjoy using breadth first search to solve problems. It's a really cool way to solve problems. And I hope you enjoyed the video, and I hope you'll join me for the next one.